Hello everyone. In this video, I have discussed the crystal field splitting in octahedral, tetragonal, square planar and tetrahedral geometry. If you find my videos helpful, then please like and subscribe to my channel. Crystal field theory considered that the bonding between the central metal and its ligand arises from purely electrostatic interaction. If the ligand are anion, the attraction will be an ion-ion interaction, and if the ligand are neutral molecule, then it is ion dipole interaction. The 5 d orbitals, which are dxy, dxz, dyz, dz square and dx square minus y square of free gaseous metal ion have same energy. They are said to be a 5-fold degenerate. If a cloud of a spherically symmetrical negative charge surrounds the metal ion, the energy of the d orbital increases. This is because of the electron-electron repulsion between the electron of metal and the ligand, but the d orbital still remain 5-fold degenerate. This is a schematic diagram of energy level. As you can see, the energy of the 5-fold d orbital remain equal both in a free and spherically symmetrical environment. Their energy equally increases in a spherically symmetrical negative charge environment. As a ligand approaches the central metal to form a complex in a particular geometry, the electron in the d orbital and the ligand repel each other. The d electron closer to the ligand will have higher energy than those further away, which result in the d orbital splitting in energy. This splitting of the 5-fold degenerate d orbital of the metal ion into orbital of different energies is called crystal field splitting. Let us consider first the crystal field splitting in octahedral complexes. In an octahedral complexes ML6, like all 6 ligands lie along the 3 axes x, y and z. So compared to the electron in the axial orbitals like dxy, dxz and dyz, electron in the non-axial orbitals like dz square and dx square minus y square face greater repulsive force. Consequently, the energy of axial orbital increases while that of non-axial orbitals decreases, due to which the degeneracy of 5d orbital gets split up into two sets, doubly degenerate Ez orbitals of higher energy and triply degenerate T2G orbitals of lower energy. The energy of Eg orbital is 6 dq above the hypothetical degenerate d orbitals, and the T2G orbitals are 4 dq below the hypothetical degenerate d orbital. The difference in the energy of the two sets of d orbital is called crystal field splitting energy, and it is denoted as delta O or 10 dq. Consider for the D1 system, the single electron would prefer to occupy one of the two T2G orbital of lower energy. So, the energy of the complex would decrease by 4 dq as compared to the degenerate state. This decrease in the energy of the metal ion in presence of ligand is known as crystal field stabilization energy or CFSE. In D2 and D3 systems, there are 2 and 3 electrons respectively. So they will also occupy low lying T2G level. Consequently, the CFSE for D2 and D3 systems are 8 dq and 12 dq respectively. However, in the D4 system, the fourth electron can occupy either Eg orbital or T2G orbital to pair one electron. The energy required by the electron to get paired up is called pairing energy, and it is denoted as capital P. If the crystal field splitting energy, that is 10 dq or delta O, is greater than P, a large amount of energy is required to excite the electron. So, the electron will prefer to get paired up in T2G orbitals to form low spin or strong field complexes. For example, if the ligand is carbon or nitrogen donor, the electron will occupy low-lying T2G level. But if delta O is less than capital P or pairing energy, the electron gets easily excited to higher energy Eg level to remain unpaired and follow Horn's rule of maximum multiplicity. The electron occupy both T2G and Eg orbitals to form high spin or weak field complexes, for example in the case of oxygen and halogen donor. Formula for crystal field stabilization energy for octahedral complex: CFSE equal to -4 multiplied by Nt2G. Nt2G is the number of electron in T2G level, plus 6 NEG. NEG represents the number of electron in EG level, plus MP. M represents the number of paired electron and P is the pairing energy. Here I have tabulated the electronic configuration and CFSE of the metal from the D1 to D10 system, both in strong field and weak field ligand environment. Keeping in mind that each electron in the T2G level contribute an extra stability of 4 dq from the barycenter, while each electron in the EG level contribute a destabilization of plus 6 dq from the barycenter. The electron in the D1, D2 and D3 system based metal always occupy low-lying T2G level irrespective of the nature of ligand, whether they are a strong field ligand or weak field ligand. Due to this, the CFSE in the D1, D2 and D3 system are -4 dq, -8 dq and -12 dq respectively. Similarly, the electron in D8, D9 and D10 system based metal always occupy high energy Eg level irrespective of the nature of the ligand. Moreover, the number of paired electron in D8, D9 and D10 system is 3, 4 and 5 respectively. Hence, the CFSE in the D8, D9 and D10 system are -12 dq plus 3p, -6 dq plus 4p and 0 dq plus 5p respectively. Now, let us consider D4, D5, D6, D7 system of strong field complex. After filling the first 3 electron in T2G of D4 system, the fourth electron has two options, T2G or EG level. Since it is a strong field complex, so the energy difference between the T2G level and EG level is very high, while pairing energy is low. So the fourth electron will occupy low-lying T2G level. Similarly, occupation of T2G level will continue until the D6 system, that is when all the orbital in T2G get paired up. In the D7 system, the 7th electron has to excite and filled in the EG level. Now consider the D4, D5, D6, D7 system of weak field complexes. Since the energy between the T2G level and EG level is low as compared to the pairing energy, the fourth electron in the D4 system get easily excited to occupy EG level. Similarly, the fourth and fifth electron in D5 will also occupy the EG level. In D6, D7, D8 system, after filling a single electron in each orbital of EG level, their remaining electrons are filled in T2G level to give a set of paired electrons. I hope now you understood the concept of filling electron in D1 to D10 systems, both in a strong field and weak field complexes. You can calculate the value of CFSE in each case using the formula mentioned in previous slide. Crystal field splitting in tetragonal and square planar complexes. In an octahedral complex, if the ligand lying on the z-axis are moving away from the central metal ion, the electron lying in the d orbital along the plane involving z-axis like dz square, dxz and dyz experience comparatively lesser repulsion from the electron of the ligand. So, the electron lying in the d orbital in this xy plane like dxy and dx square minus y square experiences comparatively more repulsion from the electron of the ligand. Thus, the order of energy of d orbital in a tetragonal complex is dyz equal to dxz, which is less than dxy, which is less than dz square and which is less than dx square minus y square. If we remove the two ligands along the z-axis in an octahedral complex, a square planar complex is obtained. So, there is a further decrease in the energy of dz square, dxz and dyz orbitals and a further increase in the energy of dx square minus y square and dxy orbitals. Thus, the order of energy of d orbitals in a square planar complex is dyz equal to dxz less than dz square less than dxy, which is less than dx square minus y square. Here is the energy level diagram of d orbitals in an octahedral geometry. As mentioned earlier, that if the ligand lying on the z-axis are moving away from the central metal ion, the electron lying in the d orbitals along the z-axis experience comparatively lesser repulsion from the electron of the ligand. So, the EG level is split up into dz square and dx square minus y square such that dz square is lower in energy while dx square minus y square is higher in energy. Similarly, the T2G level is also split up into two levels. The lower energy level consists of dxz and dyz orbitals while the higher energy consists of dxy orbitals. This overall energy level diagram represents the splitting of d orbitals in tetragonal geometry. If the ligand along the z-axis are completely removed, then there is a further decrease in the energy of dz square, dxz and dyz orbitals. The energy of dz square orbital decreases even lower than the energy of dxy orbital. The CFSE for dx square minus y square and dxy orbital is plus 1.228 delta 0 and plus 0.228 delta O respectively. The CFSE of dz square orbital is minus 0.428 delta O, while for dxz and dyz orbital the CFSE is minus 0.514 delta O. Interestingly, the energy difference between the dxy and dx square minus y square orbital is the same as tan dq in an octahedral geometry. The energy difference between the dyz or dxz and dx square minus y square orbital is delta sp, CFSE of square planar. The magnitude of CFSE is in a square planar is about 1.7 times that of CFSE in an octahedral complex. Crystal field splitting in tetrahedral complexes. Unlike octahedral geometry, in a tetrahedral geometry, the four ligands are lying between the three axes, due to which there will be more interaction with the non-axial d orbitals. Consequently, the energy of T2G orbital increases while that of EG orbital decreases, just in the reverse of octahedral complexes. The energy of EG orbital is 6 dq below the hypothetical degenerate d orbital, and T2G level are 4dq above the hypothetical degenerate orbitals. The difference in the energy of the two set of d orbital is 10 dq or delta T, that is crystal field splitting in tetrahedral complexes. The energy of T2G and EG level in terms of crystal field splitting in octahedral or delta O are plus 0.178 delta O and minus 0.267 delta O respectively. The difference between the EG and T2G level is 0.445. Thus, we can say the magnitude of CFSE in a tetrahedral is about 0.445 times that of CFSE in octahedral geometry. The smaller CFSE of the tetrahedral complex than the corresponding octahedral complex is due to the two reasons. First one is number of ligands. In tetrahedral complexes, there are 4 ligands, while in octahedral complexes, there are 6 ligands. So, the interaction ratio is 4:6 or 2:3. Second is number of energy level below barycenter. In tetrahedral complexes, there are 2 energy level below barycenter, while in octahedral complexes, there are 3 energy level below barycenter. So, the interaction ratio is 2:3. So, overall interaction ratio is 4/9 delta O equal to 0.445 delta O, which is the same as mentioned earlier from the experimental data. A tetrahedral complex with low spin configuration doesn't exist, as the CFSE is always less than the pairing energy and pairing does not take place. We can calculate the CFSE for a tetrahedral complex using the formula plus 4 N-T2G minus 6 NEG plus MP. Here I have tabulated the electronic configuration and the CFSE of the metal from the D1 to D10 system in a tetrahedral complexes. Unlike in octahedral complexes, the CFSE does not depend on the nature of the ligand, that is strong field or weak field ligand. Since the value of CFSE is always less than the pairing energy, pairing will only allow when each orbital of EG and T2G level are singly filled. I hope you understood the concept of filling of electron in D1 to D10 system in tetrahedral complexes and can calculate the value of CFSE in each case using the formula mentioned in the previous slide. 4 factors affecting in the magnitude of the crystal field splitting are nature of the ligand, nature of the central metal ion, charge on the central metal ion, and the last one is geometry of the complex. Let us discuss the first one in detail, nature of the ligand. The ligand which produce high splitting are known as strong field ligand, while those producing low splitting are known as weak field ligand. The ligand with high negative charge, small size, or capability of pi bonding approach the metal ion cause more or greater crystal field splitting. The electrostatic effect of halide ion make them weak field ligand as they are electron withdrawing, while the capability of sigma donation and pi acceptance of sigma cyanide and carbonyl ligand make them strong field ligand. Now look at the spectrochemical series, which is the series in which the ligand are arranged in increasing order of their delta O for a particular metal ion. Among the series, carbonyl is the strongest field ligand while iodide is the weakest field ligand. Consider the example of nickel with 3 different ligands. As you can see, the CFSE value are increasing as expected from the spectrochemical series. Second is the nature of the central metal ion. On moving down the group, the size of the central metal ion increases, and so does the number of electrons in the metal for interaction with the ligand, which result in more splitting. Consider the example of cobalt, rhodium and iridium complex having the same ligand. As you can see from the table, the value of CFSE increasing on going down the group. The third factor is the charge on the central metal ion. The magnitude of crystal field splitting increases with an increase in the oxidation state of the metal ion due to an increase in the polarization effect. In other words, as the charge of the metal ion increases, its ionic radius decreases. So the bond length also decreases. Consequently, there will be more interaction. As you can see, the CFSE of trivalent iron and cobalt complexes is higher than their corresponding divalent complexes. The last factor is the geometry of the complex. As demonstrated by the experimental data from the energy level diagram, the order of CFSE of a particular metal ligand complex in a various geometry is square planar, which is greater than octahedral, greater than tetrahedral. There are some limitation of CFT. CFT considered that the metal and ionic and the ligand interaction is purely ionic. However, likewise in ionic compound or salt, a partial covalent nature of the metal ligand bond is always associated and exists. CFT consider only the d orbital of the metal and does not consider the other orbital of the metal atom present in the valence shell like s, px, py and pz. It gives no satisfactory explanation for the relative strength of the ligand in the spectrochemical series. It does not consider the formation of pi bonding in the complexes. Now I end this video here. Thanks for watching. Please like and subscribe to my channel.